So for this next video, we'll look at a problem 5.27 from the homework. We're told that we have a smooth uniform bar in the figure below, and it has a mass of 22 kilograms. We're neglecting its thickness, and we're trying to find the x and y components of the reaction at A and the actual reaction at B. So again, the book is kind to us, and it doesn't make us kind of think about the type of reactions that each of these points of contact that the bar is in with its surrounding could support. But if you just think about where the bar is making contact at A, notice because of this little stub, it has the capacity to stop it from moving left to right. In addition, when the bar is actually in contact with the ground, there'll always be a normal force. So that normal force that the ground is exerting up on the bar is where the y component of the reaction is coming from at A, and the x component is coming from this little stub that will stop it from moving left. However, note at point B, it's just in contact with the wall, so there's just going to be a normal force. So that's why they're just saying the reaction at B. We know that the direction has to be normal to the actual surface. The question is just what will the actual magnitude of that be? So I'm going to start by drawing a free body diagram, and I'm going to model the rod as just a single line. I'm going to neglect its thickness as I was told to do. I'll draw in the reactions at point A and B. So I will just call this AX and this AY. In addition, I need to include the weight of the actual bar. And since we were told that it was a uniform bar, we know that the point at which we should apply the weight is going to be right at the center of the line of symmetry of this. And its weight is just going to be its mass times that acceleration due to gravity. And in addition, I know that I have a reaction at B, which I'm just going to draw actually normal to the wall. So I'm going to draw it in like this, and we'll actually determine what its direction characteristics are here in a minute. So I'm just going to call this B for now. So when I work these kind of problems, I think it's always easiest to start with an actual core rectangular coordinate system, a pure horizontal and a pure vertical axes. And if you notice what's going on here, at least the way that I think it's easiest to look at, is this wall kind of looks like it's declined a little bit from the vertical in this direction. So I'm just going to draw that in. And particularly, I'm given some geometry that tells me that this is a 60-degree angle. So I know that this angle has to be 30 degrees. If you think about the natural normal to this, it's going to be perpendicular to this surface. So the way I think about it is if the y-axis shifted in the clockwise direction by 30 degrees, that means this axis must also shift along with it to kind of stay locked together by 30 degrees. So particularly here, think about that going back 30 degrees, which gives you that 60-degree angle that you have specified. This would also be 30 degrees. And where that's valuable to me is I can say that this normal reaction at B is 30 degrees elevated in the, let me zoom in a little bit, the clockwise direction from the horizontal. And that's going to allow me to decompose this into components if I want to. I can say that B equals whatever that magnitude is times cos 30. And make sure to put a negative in to note the fact that it's going to the left. And when we do this scalar analysis, oftentimes we'll kind of float in and out of staying accurate with our signs. We'll see that here in a minute. Zoomed in too far. Sorry, I see what's going on now. My dot cam, the arm wasn't up all the way. I wondered why it was looking all weird. Sorry, you get to see me adjust it in real time. So now we have a corresponding free body diagram. So the question is, how can we actually compute what the reactions are at these points? So I'm going to say that I can compute the reaction at B by just summing all the moments about point A. And the reason that I would want to do that is if I sum all the moments about point A, then the reactions AX and AY will not be involved in a moment about that point because they actually pass through it. So that will give me an equation where I can solve for B identically. So let's think about how we would actually compute that moment. Then maybe we can draw in some lines of actions and actually think about how we would get the perpendicular distance. So if I were to note that this is a 30-degree angle, and I note that this entire distance is 4 meters, then I could actually find, remember this is actually applied at the halfway point of the center of gravity, so this entire thing, and it's not drawn to scale unfortunately, is going to be 4 cos 30. So this little bit is just going to be 2 cos 30. And this will be 2 cos 30 as well. So when I think about the rotation that the weight will actually cause about point A, hopefully everyone sees that it's going to be in the clockwise direction. So it's going to be a negative, and it's going to be whatever the magnitude of that weight is, which I'll just denote as W here. And then the perpendicular distance from point A to the line of the action of the force is just going to be 2 cos 30. Now let's think about the individual components of the reaction at B. So you notice the reaction at B is going to have a x component, bx, and it will have an actual y component, by. So let's talk about the perpendicular distance. Well, first and foremost, let's do the by component and get the sense of the rotation. If I pin at A and I push in the upward direction, so I'll assume that that will be an upward rotation. If you notice, that will cause a counterclockwise rotation, so I'll be plus by. And then what is the perpendicular distance from point A? Well, it's just going to be 4 cos 30. And then let's take care of bx. If you pin at A and kind of push in the direction that we're assuming bx is going, that will also be a counterclockwise rotation. So I'll say it's plus bx. And if you think about the distance, perpendicular distance from its line of action, it's just going to be this dimension that we have here, which is just going to be not 4 cos 30, but 4 sine 30, which is also equal to what I have here. So that basically the height, the vertical offset of B from point A. So this would be 4 sine 30. So again, I don't have to actually show that it was negative here because I took that into account when I determined the direction of rotation. So those all have to be equal to 0. And if you think about by and bx here, you actually have an expression for them in terms of a single unknown b. Because you might look at this and say, well, I can't solve that equation because I have 2 unknowns. But remember, we have expressions for by and bx. So I'm just going to rewrite this as minus w times 2 cos 30. And then wherever I see by, I'm just going to write it as b sine 30 cos 30. And then for bx, I will just remember we already took into account that negative. So b cos 30. And then don't forget we had a factor of 4 in here. So I'll write factor of 4 in here. 4 sine 30. And that's all equal to 0. And what I'm trying to solve for here is b. So I would just say b times 4 sine 30 cos 30. So that's this term here, plus b times 4 sine 30 cos 30 is going to be equal to w times 2 cos 30. So if you solve this for b, what you actually find is this is the same term twice. So you can say that b is nothing more than w times 2 cos 30 divided by 2 times 4 sine 30 cos 30. And if you do some cancellations there, you can get quite a bit of terms to cancel. And you find that this is just w divided by 4 sine of 30. And what was our weight here? It was 22. So that's going to be 22 times 9.81 to get the weight. And then we're going to divide all that by 4 sine of 30. So if we compute what that is, let me see here. So 22 times 9.81 divided by 4 times sine b of 30. And if we do that math, we're going to get a force of 107.91 newtons. And then if we round that to 3 sig figs, it'll just be 108 newtons. So once I have that expression for my actual b value, I can use it to decompose b. So I can say that b as a vector is going to be, and going back and using the results that I had earlier of minus b cos 30 and b sine 30, and you'll see the reason that I'm doing this in a minute is I'm going to just sum all forces in the x and y direction. So let me get that. It's going to be the answer that I have stored, cos 30, and then the answer times sine 30. So carrying more precision than I need, that'll be minus 93.4528 in the x direction and 53.955 in the y direction. So how will I go about determining what my reactions AX and AY are? So this is the first equation of equilibrium that I enforced. For my second equation of equilibrium, I'll sum all forces in the x direction and say that those have to be equal to 0. And basically what that's going to show me is that looking at this free body diagram, the only two forces that point in the x direction are AX in the positive direction and BX in the minus direction. So that's going to mean that AX minus BX has to be 0, which just means that AX is going to equal to BX which we've solved for here, is going to be equal to 93.4528, which, since this is a final answer, I'm going to round that to 3 sig figs and make it 93.5 newtons for the horizontal component of that. And then for finding the vertical reaction at A, I'll sum all forces in the y direction and set that equal to 0. And what that means is I have AY going up, and then I have the BY component going up as well. And don't get confused by the fact that like we had the minus in here, but remember that I accounted for it being in the negative direction when I subtracted away this force. So you have to be careful or kind of comfortable going back and forth between writing them in rectangular components and including the negative to show that they go to the left. And then when you sum all forces, if you write them in as negative, you don't want to double count it or it'll end up going back to the right in that case. So AY plus BY, we have that in the vertical direction, and that's minus W, and that whole thing has to equal 0. So what that means is that AY is just going to be W minus BY, or another way to say that is the vertical component of Y has to be whatever the weight is minus whatever B hasn't already taken care of. So that, again, will be the weight, which we have is 22 times 9.81 minus the Y component of B, which was 53.955. And if we actually compute what that is, where are we at? 22 times 9.81. And then if we subtract away 53.955, we get an answer of 161.865, which rounded as 3 sig figs is just going to be 162 newtons. So that is AY, and that is in the upward direction. Of course, this is AX, and it's going to the right. And then B, it actually has a direction that's just defined by the normal to that surface. So that's why we're just going to write that in as a magnitude. So there is the X component of A, there's the Y component of A, and there's our magnitude of B, which again is normal to the surface of that wall. So a little bit of tricky geometry, and you might want to try to, if you have extra time, to redo this and actually use a coordinate system that's actually specific to the geometry. So work in a 30-degree coordinate system. And what you'll find is if you kind of decompose each of these forces into a 30-degree coordinate system, then the component that's actual tangent to that coordinate system is going to go through A. And the only thing that will matter is the component of these two forces that are normal to the actual bar itself. And I guess one thing I would say here at the end, sorry, I was about to hit stop, is you'll find if you do that, you won't have the double trig functions inside the actual equations of equilibrium.